Hi everyone, I wanted to take a minute and go over the problems that are in the review. I'll try to keep it short and sweet, so we'll do a minimum explanation so you guys can figure out how to do each one, but other than that, if you have more questions after this video, please make sure to come ask me. The first one was from the function assignment. It wants to know if you know how to read a graph and do different operations on those functions. So for the first one, f minus g of 3 essentially says to find f of 3 and g of 3 and then subtract them. So if I look at this graph, f of 3 from the blue one is equal to 2, and g of 3 would be equal to 3. So essentially they want to know what 2 minus 3 is. So if I do that, 2 minus 3 is equal to negative 1. For number 8, they want f of g of 3, which is a composition. So if you guys remember compositions, we take 3, plug it into g, take that answer and plug it into f, or evaluate for f. So if I want to know g of 3, we just said that g of 3 was equal to 3, and then f of 3, which takes us back to that same value again, f of 3 is equal to 2. So f of g of 3 would be f of 3, which is equal to 2. For the next one, it's another composition, but this time algebraically. Remember that we're taking that inside function and evaluating f at that inside function. So everywhere I see 1 minus 2x, I'm going to substitute it into the function f for everywhere I see an x, and I get f of g of x is equal to 1 minus 2x, the quantity squared, minus 5 times 1 minus 2x plus 3. And again, I'm just substituting that value of g of x into this function f everywhere I see an x. So those are where those two things are being substituted. If I multiply out 1 minus 2x to the power of 2, I get 1, and then minus 2x would be negative 4x, and then negative 2x squared would be a positive 4x squared. If I distribute this negative 5, I get negative 5 and positive 10x. Negative 5, positive 10x. And then plus 3, and then you can just do a little combining like terms. So leading quantity would be 4x squared. I have a negative 4x and a positive 10, that's plus 6x, a positive 1, a negative 5, and a positive 3. That would be negative 4 plus 3, so negative 1. I believe, if I didn't make any errors, that that's the final answer. For the function assignment, it says I want to know what f of 0 minus f of 2 is. So if I want to evaluate the function at 0, I need to look over here at the domain and figure out which part of the domain 0 is a part of. So it's this middle part right here, because it says that x is greater than or equal to 0. So because it's equal to 0, I would evaluate here. So by substituting in 0 or plugging in 0 here, I get 0 squared, which is 0, minus 1, which is negative 1. So f of 0 is negative 1. And then if I evaluate f of 2, I'm plugging it into this top part of it because it says that x is greater than or equal to 2. So if I plug in 2 here, I get 2 plus 2, which is 4, the square root of 4, which is 2, and then 2 minus 2, which is 0. So negative 1 minus 0, which is negative 1. For the second part, I'm evaluating f of negative 4. So negative 4 would be less than 0, so it's part of this last part of the piecewise function. If I plug in negative 4 here, I get a negative 4. So negative 4 would be a positive 4. And if I substitute that in here for the square root, that would be 5 minus a positive 4, which is 5 minus 4. So that's the square root of 1, which is just 1. And the last one is a composition. So I'm evaluating f of 3. If I want to know what f of 3 is, that's a number greater than 2. So if I substitute in 3 here, that would be 3 plus 2, which is 5. So the square root of 5 minus 2. Square root of 5 minus 2. So I'm evaluating f of that now. And the square root of 5 minus 2. The square root of 5 minus 2, you don't necessarily need to know what that is exactly, as long as you know an approximate value of it, so you can figure out what part of the domain it belongs to. So the square root of 5 is a number that's a little bit bigger than 2, because the square root of 4 would be equal to 2. So this one's just a little bit bigger than 2. So if I take a number that's a little bigger than 2 and subtract 2, that's a number that's a little bit bigger than 0. So I know that that's going to be in between this interval from 0 to 2. So I want to substitute in that value here for x squared. So if I do that, I'm going to get the square root of 5 minus 2 quantity squared minus 1. When I square that, I get the square root of 5 times the square root of 5 is 25. If I do the outside terms, that would be minus 2 radical 5 minus 2 radical 5, so that's minus 4 radical 5. And then the last terms, negative 2 times negative 2 would be positive 4. And then minus 1. And last but not least, if I want to do some combining of like terms, I would have 25 plus 4 is 29. 29 minus 1 is 28. So 28 minus 4 radical 5 would be an acceptable answer without a calculator. I also wanted you to sketch the function. I know that it didn't ask you to necessarily in the summer homework, but I just want to make sure that you guys are clear on how to sketch it. So if I was going to draw a quick graph up here, and I promise this will not be perfect, but it's just a rough sketch. The square root function shifted to the left 2 and down 2 would be left 2 and down 2 would be right here, and then kind of hooked up over like this. The only problem is that they only want it when x is greater than or equal to 2, so I actually don't care about it at all over here. So I'm going to go ahead and erase that again. And then really, like I said, it's just a really rough sketch, so I'm just going to go like that. If I want to know what it's actually equal to at 2, I can plug it in. So if I plug in 2 here, I get, actually we already evaluated that. F of 2 we said was equal to 0. So if I plug that back in, it's going to look something like that. So square root function looks something like that. Then the middle piece of it is x squared minus 1. That's a quadratic function that's been shifted down 1 unit, and that's only between 0 and 2. So if I shift a quadratic function down 1 unit, this side of it would look like this. So it would look something like that. So it's only half the parabola from 0 to 2. Notice that at 2 on the quadratic function, if I plug in 2 here, 2 squared would be 4, 4 minus 1 is 3. So notice that it comes up here to 3 instead of meeting the other function here. And it's equal to at 0, which is why it's a closed circle, and it's an open circle at 2 since it's less than there. It's not equal to. And last but not least, it's equal to negative x when x is less than 0. So the function negative x has a y-intercept of 0 and then a slope of negative 1. So it just goes down like this. And it looks something like that. So I just wanted to make sure you guys were clear on how to graph piecewise functions. I wanted to make sure you knew about the open circles and the closed circles. I wanted to make sure that you knew that these don't have to necessarily meet, that we call this a jump in the graph, and we'll get to that more later on when we talk about limits. I just wanted you guys to be clear about what it looked like and how to sketch it. For domain and range, I'll quickly and briefly talk about these things. This is a fifth root polynomial. So fifth root is an odd root, and all odd roots actually have no issues with their domain. You can plug in any number that you wanted to in here, and it would be a-okay. So the only radicals that actually have issues with their domain is roots that are even. So if it was a square root or a fourth root or a sixth root. Anything else, though, has no issues with its domain as long as what's inside of it also has no issues with its domain. So the domain of number 8 would be all real numbers, which in calculus we'll typically write that in interval notation as negative infinity to positive infinity. For number 12, there is actually quite a few issues with the domain here. So the first thing is that 5 minus x has to be greater than 0 because you can't plug in negative values, or you can't have negative values underneath a radical. So 5 minus x has to be greater than 0, which means that 5 has to be greater than x, or in other words, if I rewrite that, x has to be less than 5. What else? Let's see, for log. Log is very, the domain of logarithms are that they have to be greater than 0. They can't be equal to 0, so you can't plug in 0 here, and you also can't plug in negative numbers. So another part of our domain from that log function is that x has to be greater than 0. And last but not least, because this is a fraction, it's a rational expression, or a rational equation, I should say, the denominator is not allowed to equal 0. So log of x cannot equal 0. If you want to figure out what x value would make it equal 0, remember that log is base 10. So if I have base 10 to the power of 0 equaling x, I would say 10 to the power of 0 is equal to x. And anything to the power of 0 is equal to 1, so that would be x is equal to 1. So since this is a not equals problem, it would be that x is not equal to 1, or that x cannot equal 1. So cannot equal, cannot equal. So we have 3 parts of our domain, and that comes from all 3 of those parts that have issues. So we said x cannot equal 1, it has to be greater than 0, and it has to be less than 5. So if we're going to write our domain for that problem, we would say that x has to be between 0 and 1, but not equal to 1, and then it can pick up again from 1 to 5. And that would be our final answer for the domain of this problem. Part D, even and odd functions. It just says, what does it mean for a function to be even, odd, or neither? I just really want you guys to hone in on the fact that an even function is symmetric about the y-axis. So even would be symmetric about the y-axis, kind of like a quadratic function. So if you drew a quadratic function, it would have y-axis symmetry. An odd function is symmetric about the origin. So like the cubic function is an odd function. So it is reflective across the x-axis and the y-axis. And then neither would just be if it's not symmetric about either of those. To test for it, you just plug in negative x, so you evaluate at negative x. So f of negative x is equal to, and then evaluate these 2 pieces at negative x as well. So negative 3 times negative x cubed minus 2 times negative x. And if you simplify that a little bit, negative x cubed is negative x cubed, so those 2 negatives are going to make a positive 3x cubed. And here, a negative 2 times a negative x would be a positive 2x. So the way to test for even or odd is if you evaluate at negative x and you plug it into the function, and you get the negative answer of what you started with. So notice how everything changed to sign. So negative 3x cubed turned into positive, negative 2x turned into positive. That means it's an odd function. So when that happens and you get the opposite, it indicates that it's an odd function. If you had plugged it in and it stayed exactly the same, so if nothing had changed in the original problem, it would have been even. And last but not least, if you had plugged in negative x and some things changed but some things stayed the same, it would be neither odd nor even. For transformations of graphs, this first one has been shifted to the left 1 unit and up 1 unit, and it's a square root function. So left 1, up 1 would be here, and it's square root, so it looks something like that. The second one has been shifted right 1 and up 4. So right 1, up 4 would be here. It's upside down because it has a negative, and it's stretched by 2, and it's the absolute value function. So upside down, negative, and stretched by 2 would look something like this. So the v, because it's absolute value, negative, giving it that upside down shape, and then stretched by 2. Instead of going over 1 down 1, it goes over 1 down 2. This one was not in your summer homework, but I want you guys to make sure that you know how to read graphs and how to evaluate different things on graphs. So it says evaluate at x equals 1, 2, and 3. So if I evaluate at 1, looking at the graph, at 1 this function is equal to negative 2. At 2 it's equal to 0. At 3 it's equal to 4. So that's all I mean when I say evaluate. Then alternatively solve for x when f of x equals negative 2 and 0. So that literally is asking you what... I draw a line here, what x values would make this function equal negative 2. So I've drawn a line here at y equals negative 2, and I want to know where it crosses the red quadratic function. So it crosses here at 0, and right here at 1. So the 2 x values that would make this function equal negative 2 are 0 and 1. So then for that next one, where does it equal 0? If I come back here again and draw a line at y equals 0, you can see that it intersects that quadratic function here at negative 1 and at positive 2. So those are the 2 solutions for when f of x is equal to 0. The next question was, where is it positive and where is it negative? So it's positive when it's less than negative 1 and greater than 2, and it's negative in between negative 1 and 2. So if I wanted to highlight those, it's positive wherever it's green, and it's negative wherever it's red. So you could just write those in interval notation. Last question, where is it increasing or decreasing? So this function is increasing here, wherever it's green, where it's going up, and it's decreasing here, wherever it's red, where it's going down. So from negative infinity to, that looks like 1/2, it is decreasing, and then from 1/2 to infinity, it is increasing. Alright, special factorization. For this first one, we can factor out an x. So we get x times x squared minus 25. That is a difference of two squares, so we get x plus 5, x minus 5. For the next one, we have to put it in order and then factor out a -1, because we don't like when that leading term has a negative in front of it. So if I factor out a -1 and put it in order, I get negative 9x squared, sorry, positive 9x squared, but with a negative out front. So negative of the quantity 9x squared minus 30x plus 25. And these look like pretty large numbers that you might feel like are a little out there for calculus, and that's kind of true in a sense. It ends up being an easier factorization than you might think, but typically in calculus they like to keep the numbers pretty small so you can do the factorizations in your head. But this ends up being a perfect square trinomial actually. So 9x squared came from 3x, the 25 came from 5, and the -30 came from a subtraction, and then we just squared that. So you'll notice that this is a perfect square trinomial because 3x times that -5 is -15. So from the inside and outside terms, that's how you get the -30x when you multiply that out. So that's the special factorization for that one. For the next one, there's also an x GCF, so that would be 3x squared minus 5x plus 2. If I factor this out, I get 3x here, I get an x here. I know that my last two terms are going to be 2 and 1, and the order that that would be in, if this is positive, that means they both have to be negative so that it can add to that. So it's going to be -2 here and -1 here, I believe. So that'll multiply back to a -3x and a -2x. That's perfect. Alright, and that's as far as that one goes. And last but not least, 250 and 128 both have a common factor of 2. So if I take that out, I get 125 x cubed minus 64. And that is a difference of cubes. So a difference of cubes is factored as the number that cubes to make 125 is 5. So this would be a 5x and a 5x. 5x squared. So remember the pattern for difference of cubes is that whatever number cubes to make 125x cubed goes here, and then that same number squared goes here. So that would be 25x squared. For 64, the number that cubes to make 64 is 4, and then you square that and put it back here, so that's 16. And then to find that middle term, you just multiply a and b together. So 5x times 4 is 20x. Sorry, it's getting a little tight in here. And then the signs, you keep the same sign first, so this is going to stay negative. Then you change it for this one, and then this one's always positive. So it's going to be a negative, a positive, and this one's always positive. And that is how you factor out that difference of cubes. For this linear function, it says write the equation of the line through the point that's parallel and then one that's normal. So a parallel line would have the same slope. So first of all, if I want to find the slope of this line, I need it in slope-intercept form. So that's going to be y equals -x plus 4. So the slope would be -1. So a parallel line that goes through this point, 5, -3, and has this slope would be y minus y1 equals the slope, -1, times x minus x1. I'm going to be real honest with you, and one of the things you're going to learn about calculus is we never want to have our answers in slope-intercept form. We always want to keep them in point-slope form. So I actually encourage you to leave your answer like this and not to put it into slope-intercept form. It'll just be very helpful and you won't make as many mistakes. And then the second part of it for part B, it says the normal to the given line, and normal just means perpendicular. So the perpendicular slope to -1, the perpendicular slope would be the opposite reciprocal, which is a +1. So that would be y plus 3 equals 1 times x minus 5. And again, don't worry about writing it in slope-intercept form. You can keep it in point-slope form. To solve these quadratics, we're going to factor the first one. So the first one factors 2. Oops, go back. First one factors 2. X plus 9, x minus 2. So my two solutions are x equals negative 9 and x equals positive 2. For the next one, I would probably solve by taking square roots. So if I add 72 to the other side, I get 2x squared equals 72. If I divide both sides by 2, I get that x squared is equal to 36. And if I take the square root of both sides, I get that x is equal to the positive or negative square root of 36, which is 6. For letter D, bring everything to one side. So that would be 12x squared minus 5x minus 2 is equal to 0. If I want to factor that, I get 4x plus 1 and 3x minus 2. And then if I solve that, I get x is equal to negative 1/4 and x is equal to 2/3. That factorization, by the way, hopefully you guys are doing factor by grouping for stuff like that, or whatever method you know on how to factor. So I didn't show the work for it, but hopefully you guys are good on that. And like I said, for the AP test, they don't usually put very big numbers. They keep it more problems like number A, or letter A, I should say. All right, for asymptotes, it says find any vertical or horizontal asymptotes and if present, the location of holes for the graph. On this first one, we don't have any holes because there's nothing to factor. The horizontal asymptotes, because this is x to the first power and x to the first power, the rules are if the degrees are the same, then the horizontal asymptote is at the ratio of the leading coefficients. So because the degrees are the same and there's a 1 coefficient up here and a 1 coefficient down here, then the horizontal asymptote would be at y equals 1 over 1, which is 1. Y equals 1. I'm going to go through really quick and just do all of the horizontal asymptotes just so that we can remember how to do those. For the next one, the degree on the top is 0, the degree on the bottom is x squared, so therefore the horizontal asymptote would be at 0 because the degree of the denominator is greater than the degree of the numerator. So horizontal asymptote at y equals 0. For the next one, the degrees are the same again, x to the first and x to the first, so that would be 2 divided by 1, which is 2. So horizontal asymptote at 2. For this one, the degrees are the same, 2 squared and squared, so the leading coefficient being divided would be 2 over 1, which is 2. So horizontal asymptote at y equals 2. For number 5, the leading coefficient, the leading term on top has a degree of 1, on the bottom it has a degree of 2, therefore horizontal asymptote at 0. And for the last one, I know it's kind of hard to see up here, but the leading coefficient on top is a 2, on bottom it's also a 2, so the leading coefficients when I divide would be 1/2. So horizontal asymptote at 1/2. Alright, now we go back and do the vertical asymptotes. So for the vertical asymptote, we're looking at all the zeros of the denominator that are not holes. So this one has a vertical asymptote at -5. So x equals -5. This next one, there's no holes as well because nothing factors, so the denominator would give us a 0 at 0. So it has a vertical asymptote at 0. This next one, if I factor a 2 out of the top, I get 2 times x plus 8. So there actually is a hole. There's a hole at x plus 8, or at the factor x plus 8, which is x equals -8. And because of that, once it does simplify, there is no longer a vertical asymptote there. So our hole is at x equals -8. So hole at x equals -8. And to find the actual location of that hole, like the point that it's at, if you plug -8 back into the function after it's been simplified, so once I get rid of x minus 8 on top and bottom, I'm left with 2. So if I plugged -8 back into an x there, I could have evaluated it, but there are no x values left after I simplify the x plus 8, so it's just 2. So if I wanted to write that as a point, it would be -8, 2. For this one down here, if we factor on top and bottom, you could do the same thing. If it's okay with you guys, just for time's sake, I'm going to skip past those last ones. You guys can check the answers on the worksheet, but the same process you're going to go through. So factor everything. If anything simplifies out as a common factor, that's a whole. And if nothing simplifies out or if something's left behind in the denominator, that would be your vertical asymptote. All right, negative and fractional exponents. It says simplify and write with positive exponents. So for the first one, to simplify negative 12 squared, that would be negative 144. And then this negative exponent, x to the negative 5, is only applying to the x, not to anything else. So that's the only thing that gets moved to the bottom. So x to the positive 5. For the next one, notice how negative 2 is applied to everything. So everything in here is going to move to the bottom, and it's all going to receive a power of 2. So 1 over negative 12x to the 5th quantity squared. And then everything receives that power of 2. So that will be 1 over negative 12 squared is 144. And x to the 5th squared would be x to the 10th. And for this next one, because the division has the exponent of negative 3, everything is also applied to that. So the negative 4 moves to the bottom with a new exponent of 3, and x to the 4th moves to the top with a new exponent of 3. So it kind of just flips upside down as the reciprocal, x to the 4th over negative 4. And that's all with a new exponent of positive 3 now. And if I apply that to everything on the top, x to the 4th raised to the 3rd power would be x to the 12th. And on the bottom, negative 4 raised to the 3rd power would be negative 64. All right. To eliminate complex fractions, you would multiply by the least common denominator. So I'm only going to do these first two if that's okay with you guys. I'm not going to do that last one. So here I'm looking at all these little mini fractions, and I'm looking for a least common denominator. Let me put the brackets here instead, actually. So if I have a 2, a 5, and a 4, the least common denominator between 2, 5, and 4 would be 20. So if I multiply everything on the top by 20, and everything on the bottom by 20, that's going to help me to eliminate these complex fractions. So on the top, 2 times 20 is equal to 40. 7 times 20 and then divided by 2, I like to do that simplification first in my head and then just multiply whatever's left. So the 20 divided by 2 would be 10, and if I distribute the 10 to the 7, I get 70. Between 20 and 5, if I divide 20 by 5, that would be 4. So if I distribute 4 to the 3, that would be 12. On the bottom, 20 multiplied times 5 is 100. And then 20 divided by this 4 would be 5. So if I distribute 5 to this 3, I get 15. So minus 15. And then if I add all these things together and do all that subtraction and addition, that would be 70 plus 40 is 110. 110 plus 12 would be 122. And then on the bottom, 100 minus 15 would be 85. And leave it like that. And then I'll also do number 4. Hopefully you guys are okay with 5 once we do number 4. So if I'm looking for the least common denominator of the top and bottom, that would be an x, because this one has an x and that one has an x. If I multiply that, I get, in the numerator, x times x, which is x squared. And then if I multiply x here, I get x over x, which is 1. So x squared minus 1. On the bottom, if I distribute the x, I get x squared and then plus 1. And that doesn't simplify anymore. That's as far as it goes. For this one, hopefully it's very similar to number 4 for you and it's not too much different. The only thing I'll mention is that these aren't written as fractions necessarily, but you can change them. So this would be the quantity 1 plus 1 over x, and then down here it would be 1 minus 1 over x squared, and you could look for the common denominator and multiply it that way. Inverses. To find inverses, we switch x and y. So this would be x equals the square root of 1 minus y cubed. And then do the opposite things in the opposite order. So to get rid of the square root, I would square both sides. So that would be x squared is equal to 1 minus y cubed. And then I would subtract 1 from both sides. So x squared minus 1 is equal to negative y cubed. And then divide both sides by that negative. So you'd have negative x squared plus 1 is equal to y cubed. And then last but not least, take the cubed root of both sides. So I'd have the cubed root of, and then if I rearrange these, that would be 1 minus x squared equals y. And that would be the inverse, so y inverse. Perfect. Adding fractions and solving fractional equations. To get rid of, if you have an equation with a bunch of fractions in it, to get rid of all those fractions all at once, you can multiply by the least common denominator. So if I multiply, oh my gosh, there we go. If I multiply everything by the least common denominator, that would be 6x. So between 3 and 6, that's a common denominator of 6. And then with the x, we distribute these. So if I distribute it all the way over to the left, 6x times 2, but then divided by 3, remember? So if I simplify first, 6x divided by 3 would be 2x. So if I multiply that, would be 2x times 2, which is 4x. On the second one, the 6x and the x are going to simplify to be 1. So then I just distribute the 6, so minus 6. And then on the last one, we have 6x over 6, so I'm left with an x times 5, which is 5x. If I solve this equation, I subtract 4x from both sides, so I get that negative 6 is equal to x. And then if I wanted to check to make sure that was not an extraneous solution, I could plug it back into the original problem. If I plug in negative 6 here, I don't have any issues with my domain, so we're good to go there. Alright, solving absolute value equations. The main thing I need you to know with absolute value equations is that the absolute value allows it to be a positive or a negative 7. So that's essentially what absolute values are doing, is allowing whatever's inside of them to say this is equal to positive 7 possibly, but it also could have been equal to negative 7, and then the absolute value bars changed it to be positive. So we have to take both of those into consideration. It could have been x squared minus 2x minus 1 equals that positive 7, but it also could have been x squared minus 2x minus 1 is equal to negative 7. And then to solve this, you just solve it like we did the previous equations, where you bring everything to one side. X squared minus 2x minus 8 equals 0. X squared minus 2x, and then if I add 7, I get plus 6 is equal to 0. And then you would factor and then continue to solve. Again, for time's sake, I won't finish that. I'll let you guys do that on your own, and then check your work on the solution guide. This is one that I'm pretty sure you guys have not really covered in previous years, so I'll try to spend a little bit more time on this one to make sure you guys are all clear. When I've taught students how to solve inequalities in the past that are nonlinear, so because this is x cubed and x squared, this is a nonlinear inequality, I always teach them to make it an equation first in order to solve for what values would make it true as an equation, and then graph it and figure out the answer graphically. So here's what I mean by that. I would change this to be x cubed is equal to 4x squared, and then I would solve that equation. So bringing everything to one side, I would get x cubed minus 4x squared is equal to 0. That has a GCF of x squared, so I could factor it out as x squared times x minus 4, which means I have two solutions. I have a solution at x equals 0 and a solution at x equals 4. From there, I would go ahead and graph this. So I would say, okay, I have a 0 at 0, a 0 at 4. I know that this is a cubic function. This is an x cubed function, which goes up to the right and down to the left. And last but not least, using my knowledge of multiplicity, I know that at x squared, which is the 0 root, it's going to bounce since it's an even multiplicity, and x minus 4 is an odd multiplicity. It will cross. So I'm going to go ahead and bounce here and cross there. The reason I really like students to graph it, it is possible to do it by plugging in test values that are around 0 and 4, but a lot of times students can make mistakes if they're going too quickly, or in my opinion, if you're strong with multiplicity and graphing polynomials, then it's much easier and more accurate to graph it. So at this point, I come back to this, and at one point I had changed it from a less than symbol to an equal to symbol, so I'm just going to go back and change those all back to less than symbols again, so that we can evaluate what this function would look like at that point. So now what I'm going to be looking at is right here, and I'm going to say, okay, I graphed this function, and I want to know where this function is less than 0. So less than 0 just implies that it's negative. So this function is negative here, and it's negative here. It's not negative greater than 4, and it's also not negative here because it's equal to 0, which is not the same thing as being negative. So my answer for this inequality would be from negative infinity to 0, union from 0 to 4. And we are going to get a lot of practice with that this year. You guys will have a unit in calculus that this becomes very, very helpful in. All right, exponential functions and logarithms. This first one, if I rewrite this, this would be ln of e to the negative 2/3. So negative because it was in the bottom and I brought it up to the top, and then 2/3 because it has a power of 2 and a root of 3. And remember that it's that property of logarithms that if the base is the same, this is log base e. If the base is the same as this base, then we can say that the exponent is our answer. So negative 2/3 is the answer there. And then similarly, if the base of the exponential function is the same as the base of the logarithm up there in the exponent, same thing, it's equal to 12. If you want to see the reasoning for that, for the first one, I would say, okay, ln is the same thing as log base e of e to the negative 2/3. And so I always ask students, I say, okay, do you know what that's equal to? And before they are able to know this property, they might not, and that's okay. So we would say, okay, let's go back and convert this into exponential form. I say you might not know what it's equal to, but it's equal to some number. So let's set it equal to x. And then when I teach this, converting to exponential form, I teach the wraparound. So I take the base and wrap it around to this side, and it's equal to that. So e to the power of x is equal to e to the power of negative 2/3. I know in previous math classes, some of you guys may have heard of that as the swoop-de-whoop or something like that. But in my class, I call it the wraparound, so we might interchange those. Anyway, the moral of the story is we have the same base now, and we know that if this has a base of negative 2/3, then x must be equal to negative 2/3. So coming back up here, I would say, okay, I didn't know what it was equal to before, but now that I've written it exponentially, I know that log base e of e to the negative 2/3 is negative 2/3, because that's what x is equal to. So that's the long way of explaining how to get that. The other thing I want to make sure you know of is I want to make sure that you know the key features of the exponential and logarithmic graphs. So I will quickly sketch those. So I want to make sure that you know that the exponential function goes through the point 0, 1 and 1, e. 1, e and 0, 1. And that it has an asymptote at y equals 0. So if I graph an exponential function, it looks like that. So I need you to know those three things. I need you to know there's an asymptote at y equals 0. I need you to know it goes to the point 0, 1, and I need you to know that it goes to the point 1, e. So this is y equals e to the x. Then the logarithmic graph, I need you to know three things about that one also. I need you to know it has an asymptote at x equals 0. It goes through the point 1, 0, 1, 0, and it goes through the point e, 1, e, 1. And it looks like this. So if you know those three things, and this is y equals ln of x. If you know those three things about both of those graphs, then you're golden. So again, exponential goes through 0, 1 and 1e, and then alternatively for log, it's the opposite, 1, 0 and e, 1, and that's because those are inverse functions. All right, right triangle trigonometry, it says there's kind of a typo there, but let P be a point on the terminal side of theta. Find the 6 trig functions of theta, and answers do not need to be rationalized. So if I'm looking at this angle, theta, and I draw it in the coordinate plane, that means that this is the point 15, 8. And if I look at that in the coordinate plane, it creates a triangle. 15 is the x-coordinate, and 8 is the y-coordinate. So the x-coordinate is how far over I go, and 8 is how far up I go. If you use the Pythagorean theorem to find the missing side, the hypotenuse, you would get 17. And then I just need you to know SOHCAHTOA from there. So if you guys remember SOHCAHTOA, sine would be opposite over hypotenuse, so 8 over 17. Cosine would be adjacent over hypotenuse, 15 over 17. Tangent would be opposite over adjacent, so 8 over 15. And then I also want you to know the other three, so the reciprocals of them. So the reciprocal of sine would be cosecant, so just flip the hypotenuse over opposite instead. The reciprocal of cosine is secant, and the reciprocal of tangent is cotangent. So I'm not going to write all those out. You guys can check them in the notes, but that's how we figure that out. Solving trig equations and inequalities. For the first one, I would probably divide both sides by cosine squared of x. By doing that, on the right-hand side, cosine squared and cosine squared make 1, and then we get 3 left over. On the other side, on the left, we have sine squared over cosine squared, which is tangent. So that's actually tangent squared of x. And then if I wanted to solve for tangent, I could take the square root of both sides. So I have that tangent of x is equal to the square root of 3. And that's a plus or minus. From there, if I want to know where tangent of x is equal to plus or minus the square root of 3, you could look at your unit circle. And so tangent, which is sine over cosine, would give us all the pi over 3 angles. And so x would equal, if I'm listing all of them in the first revolution, that would be pi over 3, 2 pi over 3, 4 pi over 3, and 5 pi over 3. Because it's the positive and negative radical 3's. On the next one, you could do the same thing where you divide both sides by cosine. You get that tangent is equal to 1 and go through that same process and looking at the unit circle. But honestly, on these ones, I would like you to start thinking bigger picture. So I just want you to think of the unit circle in your head and think, where does sine equal cosine? So if you can think of the unit circle in your mind, in order for sine and cosine to be equal, they have to be the same sign. So all the trig functions are positive in the first quadrant. Sine and cosecant are positive in the second quadrant. Tangent and cotangent are positive in the third quadrant. And cosine and secant are positive in the fourth quadrant. So if I want sine and cosine to be the same sign, since they're going to be equal, they have to be either in the first quadrant where they're all positive or in the third quadrant where they're all negative. Now if you can think of the unit circle, for example, at pi over 6, that's 1/2 comma radical 3 over 2. So obviously they're not equal there. If I think of the next one, pi over 4, that's radical 2 over 2 and radical 2 over 2. And that's the first time that they are equal to each other. So pi over 4 is one of my answers, and then over here in the third quadrant, that same reference angle in the third quadrant would be 5 pi over 4. So my two answers are x equals pi over 4 and x equals 5 pi over 4. And like I said, you're able to figure that out algebraically this way, but sometimes it just kind of makes more sense to think about it in terms of the unit circle and to use your deductive reasoning to figure out the answers there. Alright, for this one, some of you guys may feel comfortable using the unit circle. And some of you guys, I believe, if I remember correctly, know this from the left-hand rule. And the left-hand rule is a little bit difficult to display without seeing me. It's hard to do over an interface like this. So in class, I'll have to explain what the left-hand rule is. But in my opinion, it helps a lot. Just that way you don't have to draw the unit circle every time. If you accidentally make a mistake on the drawing your unit circle, it would kind of mess you up for all your other problems. So the left-hand rule, in my opinion, is a little bit more foolproof and faster and more accurate. So I'll teach you guys how to do it in class tomorrow. But essentially, you just have to answer two questions. Question 1 is which quadrant would that angle be in? So 2 pi over 3 would be in the second quadrant. And sine, if I come back to my ASTC, and if you guys haven't seen this before, it's an acronym. All students take calculus. The A stands for all functions are positive, all trig functions. The S is sine and its reciprocal. The T is tangent and its reciprocal. And the C is cosine and its reciprocal. So it tells you which functions are positive in which quadrant. So 2 pi over 3 being in the second quadrant means that sine is positive. So that's the first thing I want you to ask yourself. For the next one, 7 pi over 6 is in the third quadrant, but cosine is not positive here, so I would say this one's negative. And then 4 pi over 3 is in the third quadrant as well, and so tangent is positive there. So I would say, okay, great, tangent's positive. So that's the first thing I would always ask myself, is it in positive or negative depending on which quadrant it is in. The next thing you need to ask yourself is what reference angle it is. So this first one is over 3, so the reference angle is pi over 3. This one's over 6, the reference angle is pi over 6. And this one's over 3, so the reference angle is pi over 3. And then, like I said, tomorrow I'll teach you the left-hand rule. So when you hold down your pi over 3 finger using your left hand, and I'll explain what that means in class, you would know that sine is equal to radical 3 over 2. If I hold down my over 6 reference angle, I would know that cosine is equal to radical 3 over 2. And last but not least, if I hold down my over 3 reference angle and look at tangent, which is on the back of your left hand, and again, this makes no sense if you have no idea what I'm talking about, so I'll explain it in class, but that would be radical 3 over 1, so just radical 3. So, like I said, pretty easy to figure out the trig ratios without needing to have a unit circle. I will definitely teach this to you guys because I strongly recommend knowing it for all of our tests and the AP test. And that was the last slide. All right, thank you so much for watching.